All right. So welcome everybody. This is Flow seminar, where Flow stands for Federated Learning One World, which was a seminar created to provide a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. And today it's my great pleasure to introduce our speaker, Arto Maranjyan, who is a PhD student at KAUST, advised by Professor Peter Richtari, focusing mainly on optimization for machine learning and federated learning, with a specific focus on distributed and randomized algorithms. And today he's going to tell us more about his recent work on the first asynchronous SGD with optimal time complexity. Thank you, Arto, for agreeing to give a talk, and looking forward to that. Please, floor is yours.
Thank you, Sam, for the nice introduction. Okay, so imagine we are training a machine learning model on two devices, let's say two GPUs. Now, what happens if during our training, one of these GPUs, they just die for some reason? Now, if we were using a synchronized approach, that is, if we were asking, let's say, these GPUs to calculate the gradient and then take the average and do a gradient descent step, then we are screwed. We cannot continue our training anymore, because if one of them is not there and your algorithm requires both of them to be there, so if one of them is not there or the time is infinity, then you are screwed. You cannot do your training. So we would like to have a method which does not require synchronization. That is, it's asynchronous. And let's say we care about stochastic gradient descent. Now, let's say we have a deadline. Let's say we want to submit, we want to finish our experiments for new reps. So we want our method to be as fast as possible. Or in other words, we want this to have optimal time complexity. So I'll be presenting Ringmaster, which is the first such method. It is the fastest first order asynchronous method. So let me give the outline of the talk. I'll first start with the problem setup. What is the optimization objective that we are trying to solve? I'll talk more about this heterogeneous system, this cluster of GPUs or whatever, and then we'll talk about the method, the SGD, and how can we parallelize SGD in this system. So we'll first talk about the different ways of parallelizing this SGD, as I said. So first approaches would be synchronized. We'll discuss 3 synchronized approaches, and then we'll arrive to asynchronous SGD. We'll talk then what are the problems of asynchronous SGD, and we'll solve these problems with Ringmaster SGD. Okay, so let me tell you that this talk is one of the series talks for asynchronous SGD. The first part was given again on Flow last week by Peter Richtari, and you can watch this talk in YouTube. And despite the fact that this is a series of talks on asynchronous SGD, you don't really need to know what's this talk about, the Peter's talk about, to understand my talk. So you can understand it completely independently, but there will be some overlaps, but that's not too much. And there will be also other talk by Sasha, maybe in near future, again on asynchronous SGD. All right, let's start. So this is the objective function that we are trying to solve. We are interested in this stochastic optimization, where we have this fx xi is a loss function of data point xi, and we have some distribution of this xi. Let's say if we are doing some image classification, then this D would be all distribution of all possible images, let's say of cats or dogs. Or we can also recover the empirical risk minimization if we assume that this D is finite. So we'll have this. Our objective would be this average empirical risk. So this is the problem that we are interested. Now, what about the method? And the most simple method for solving this problem would be SGD. I guess everyone here knows what's SGD, but let's just quickly go over it. We have this iterative process where every time we decrease our current iterate by with some learning rate gamma and multiply with the unbiased estimator of the gradient at point xk. And this unbiased estimator can be different. So the simplest one would be gradient at a single data point xi here. Or you can take some mini batch So you can take B, these data points, and take the average of those. So obviously the second one is better than the first one. And just because for the second one, the variance is smaller, and it would be, let's say, sigma divided by b times smaller than for the first time. And if you use the second one, you would need less iterations to converge. And the method will look like this. You'll start somewhere from the top of your loss curvature and you'll go down. Okay, now what about this heterogeneous system? So we assume we have these different devices. For simplicity, let's say we have 3 devices. And these devices they have different computational power, they have different computational speeds. And we assume that we can ask them to compute a gradient at a single data point. And we do one assumption that all of these devices, they have the same shared memory. That is, all of them, they have access to this D, the distribution for size. And everybody can compute unbiased gradient estimator, that is, I mean, for each single xi. But as I said, that the speed of these devices is different. So every time we ask a device to compute a gradient, it will take tau I time, and these tau i's are different. So in this case, tau 1 would be the smallest one, the fastest device, and tau 3 would be the slowest device. So the question would be, if we want to do SGD, how can we do SGD if we have these resources, that is, if we have these devices? And more specifically, the question would be, how do we construct this G, which was the unbiased estimator? And as I said, there are different ways of constructing it. The simplest one would be to take the single gradient of a single data point, or you can take some mini batch, and mini batch is preferable because it will lead less iterations. So let me pause here for a moment in case you have some questions.
Yeah, I don't think there are any questions, no questions in the chat. I think it was very clear so far.
Okay, good. I mean, this part is kind of repetition what Peter said last week, so maybe that's why there are no questions. And the next part will also be some kind of repetition. But anyway, let's go over this. So what would be the simplest approach if you want to use these devices and to do SGD? It would be to take the fastest device and to simply ask gradient always. Yes? Was there a question? Okay, I guess not.
Oh, it was my
So,
side.
okay, so we take the fastest device, and in this case, it would be the device for which the computation time would be tau 1 every time. And every time we will be asking only this device to give us a gradient at random xi. So every time this device will sample a new different xi and return new gradient. And the time for this training would be tau 1 times the number of iterations you take. And since you are using only a single gradient, your gradient estimator is not good, and you will need more iterations. But still, you are using the fastest device. But the problem here is that you are not using the other devices, which could also do some computations and potentially could benefit you in this case. But nevertheless, this method is not that bad, because if you have, let's say, 2 devices and in the beginning, as I said, one of them is not working, or in other words, the tau for the second device, let's say it's infinity, then this is the best you can do. You will simply take the device which you have, which is available, and you run SGD on it. Now, but if it's not this extreme case and you have some workers which can compute something, they are not that bad, maybe there is a better approach of using these devices. And that approach can be this mini batch SGD, where every time, instead of asking only the fastest device. You ask all of your workers, all of your available workers to give you a gradient, and you simply take the average of these gradients and do your SGD step. So in this case, if n, we have 3 devices, n is 3, and so in each iteration, we will receive gradient at different psi I k's from these devices, and we'll take the average and do a step. Now, what's bad about this approach? It is that each iteration depends on the slowest device, and in this case, tau 3, and there will be this gap where the fast devices will not do anything because they will be just waiting for this slowest device. And again, if this tau 3 is very big, if it is infinity, then you will do only one step or you will not do any step because this algorithm says that you have to synchronize, you have to use all of your devices. Okay, are there any questions? Everything was covered by Peter until now. Okay, so Peter also talked in his talk, how do we fix this? And the fix would be very simple. So because if you look at this algorithm, there is nothing that says that you have to use all of your devices and you have to use all of them just once. Since all of these devices give you the same kind of gradient, they are all have the same, they are all unbiased and they have the same variance. You don't really care which device gives you gradient, so you can simply ask one device multiple times or whatever. And this approach would be this Renal SGD, where you say instead of requiring n gradients, let's say you require p gradients, and I don't care which one returns me this gradient. And if you have these conditions, what is the fastest way to collect these p gradients? That would be this asynchronous batch collection. So you say, I want 4 gradients in this example, and you simply wait until your workers send you the gradient. So, and they will do, every time they will finish computation, they will send you the gradient and start immediately a new gradient computation at different point psi. And after this, you'll just synchronize all of them and do this asynchronous mini batch collection again. But again, there is a problem here, and the problem is that some of these devices will do wasteful computation. I mean, they will do some computation, but they will not finish because at that time you will receive your required gradients, these big gradients, and I mean, this time would be wasted in some sense, and you will have these gaps. Okay, now we say, so these gaps in all of these 3 methods, we always have these gaps. And the reason is that we always require synchronization. And these gaps are unavoidable if we have this requirement. And I mean, we will only have, remove these gaps only for homogeneous case if we have this tau 1 and tau 3, if they are all the same, then we will not have these gaps. But in general scenarios, we will always have this. Now we just say, what if we simply remove these gaps and try to deal with this method and see what we can do, what we can do about this. And so if we remove these gaps, we will have this picture, and this will be asynchronous SGD. But the problem with this method would be this is no longer SGD, and you cannot write the updates of this method as SGD, basically, where you have this gradient estimator at point xk. And the reason is because this method behaves like every time you receive a gradient, you do an update. And at some point, you can receive a gradient which is not at your current point xk because other devices did updates already. So you have some delay there, and the gradient estimator is not at point xk, but some an older point. Okay, let me explain this more on a simple illustration. We have again these 3 devices. And let's say in the beginning, we ask all of them to compute gradient at the point x0. And let's say the first worker finishes its computation, it sends you the gradient. Then the server does the step with this gradient and returns back the new updated point to the worker that sent the gradient. And this worker starts immediately computing gradient at this updated point x1. Now, and in the second iteration, let's say you receive gradient from the second fastest guy, and then you again do update, but now notice you are updating your point x1 with gradient which comes from point x0. And so you introduce some delay here. And the delay, we call it delta, and depending on the iteration k. And it's simply the difference between your current point and the point for which you receive the gradient. So 1 minus 0 in this case. And then again, you will send this new updated point to the worker and we'll continue this process. And let's say at the end, if you receive from the other worker, you'll have delay of 2. And in general, you can write this asynchronous SGD method in this simple formula. This looks a lot like SGD, but with the only difference is that you have not gradient of at xk, but with some xk minus delta k. And this delta k, if it's 0, then you have simple SGD. But it can also be very big. It can be as big as your total number of iterations. So imagine a scenario that in the beginning you asked all of your workers to compute gradient. You are doing this updates, and at the final step of your iteration, you receive a gradient from the worker, which you asked in the beginning. Maybe let's say it's total k, big K times slower than all your workers. So this will happen. Okay, let me pause here again. In case if you have questions about this method, asynchronous SGD. Okay, I'm hoping everything is clear. That's why I don't have questions. There are two cases, either nothing is clear.
I think it's been very clear so far.
Okay, good.
No worries.
We have something on chat. Okay. All right, let me continue then. So this is asynchronous SGD. And this was first introduced in this paper, Hogwild, in 2011. And they also received Test of Time Award, New Test of Time Award at 2020. So this was a very influential paper, and since then there were lots of research on this. And let me just show this timeline. So it's first in quotation because in optimization literature there is also methods also devoted to asynchronicity, even earlier than this Hogwild. But let's say it's first introduced in machine learning community. Okay, since then people were trying to understand this asynchronous SGD because it was not clear why it's good from theory perspective. And I just highlighted important milestones, let's say. And the first one was this 2022 by Koloskova and Michigan. There are two different papers which study this ASGD, and they introduced this delay adaptive SGD. And this was the first type of asynchronous SGD which was better than simple mini-batch SGD in terms of time complexity. Before that, there were many asynchronous methods, but it was not clear that this method would be better than just doing mini-batch SGD. And the reason was that that there was no time complexity basically. There was just iteration complexity, and the iteration complexity was depending on this delay. And as I said, this delay can be very big. And if you have that type of complexity, it's not clear if it's better than mini-batch SGD or not. So the first one was this delay adaptive SGD, which they showed that in fact it is better in terms of time complexity than simple mini-batch SGD. And then 1 year later, from our group, Renal SGD, and Peter was also talking about this method last week, and they showed that you can do even better than this delay adaptive SGD by doing this semi-asynchronous SGD stuff, and which was you're doing this asynchronous batch collection, but you still were doing synchronized steps. So this was Renal SGD. And then we go one step further. We say it's not semi-asynchronous, it's fully asynchronous SGD. And that's going to be the ring master, and it will achieve the same time complexity, the optimal time complexity. Also, Renala also achieves optimal time complexity, but it will be fully asynchronous. Okay, now about Hogwild. I'm not sure why it's called Hogwild, but I'm just assuming that the algorithm itself is kind of wild. It does these wild updates with big delays, and if you think about them, it's not even clear why the method works. So let me illustrate this idea on a simple example. So let's consider this simple function, x squared plus 5y squared. This is the contour lines of this function. And now let's say we want to find the minimizer, which is 0, 0 point, and we are doing this by simple gradient descent. We start at some point x0, and we do this zigzag updates. It's because the gradients are vertical to your contour lines, it will look like this. And now let's say at iteration x5, you will receive a gradient, which is like 5 iterations, which has delay of 5. That is, it will be gradient at point x0. And this is realistic scenario. If you have, let's say, two workers, one of them is 5 times faster than the other one, then this is exactly what will happen at your point x5. You will receive gradient at the point x0. And if you do this update, you will go there, basically. And this looks very bad because you will do 6 iterations and your function value will be almost the same as as in the beginning of your iterations at x0. So you did 6 iterations, but you basically did nothing because you didn't decrease your loss value. So it seems that this method doesn't even work, but it does if you introduce some fix to it, and the fix would be just to simply have small step size for this delays. So if you divide by, let's say, 5, and 5 is the number of delay actually, you will do this type of updates, and this doesn't look that bad. So eventually you will converge, but of course it will take you longer if you didn't have these delays. Okay, now what do we say? We say what is the idea behind this ringmaster HGD? We say that this ring hog wild is very wild. It does these crazy updates, and these crazy updates come from big delays. And we just say that we need to somehow tame this wild behavior, and potentially it will be beneficial. And that's what we do. We introduce ringmaster, which tames this hog wild. And the idea is we want to control this delay, so we have smaller delays. And that would be the core idea of ringmaster, basically. So let me show why small delays are good. So just in this example, so instead of having a delay of 5, if you had delay of 3, let's say, you would do this kind of update, which is already better than if it was 5. And on top of this, if you had a smaller step size, you would do even better updates. So this is the core idea of ringmaster for not allowing very big delays. Now the question would be, how can we control this delay? How do we do this? Okay, let me pause here again. Is it clear what we're trying to do?
Yeah, I mean, I think what you described is quite clear.
Okay, so how can we control this delay? Any ideas?
I
I want
mean,
to get some
potentially you could
interaction.
ignore there is a large delay, right? Like you can ignore those updates.
Yes, that's very good. Yeah, that would be the second idea. The first idea, the simplest idea, would be, so if we have these devices, and what is the reason of having these big delays? The reason is that you have slow workers. So if you remove some of your slow workers, say if you remove this slowest worker, then you will not have big delays, you will have smaller delays. And it turns out that this idea is not that bad. And in this deterministic scenario where you have this tau i's for each device, then there is a formula for which allows you to set the number of workers, or in other words, the workers that you want to remove. So if you use only these workers, then you will have the optimal time complexity. Now, what this formula says, so you have some uh, here the sigma is the variance of your gradients, epsilon is the accuracy you want to achieve, and so you have some quantity depending on the harmonic mean of these times, and this is something depending on sigma and epsilon. And m is the number of workers you want to use, and these tau i's are sorted increasingly. Yes, increasingly. So the tau 1 is the fastest device, and you just want to find the fastest m workers that will minimize this magical quantity. So if you do this and you use only those first m star workers, then you will have optimal time complexity. Now, the problem with this is that you don't know these tau i's, and on top of that, these tau i's can change throughout your training process. So you want a method, an approach for, in some sense, choosing these optimal workers throughout your training. If these tau i's change, you also want to change uh, your participating workers. And as Samuel said, how can you do this? A very simple idea. You can simply, by ignoring all the gradients, you will achieve this basically. Okay, let me show what I mean by ignoring all the gradients. So let's consider again this asynchronous SGD. Every time we receive a gradient with some delay delta k from some worker, we don't care which worker sends you this, but the gradient has delay of delta k. So it sends this gradient to the server, and server simply checks if this delay is smaller than some threshold, and we call this threshold R. If it is smaller than this threshold, then we will apply this gradient and we'll do the simple asynchronous SGD step. If not, then we ignore this gradient. We don't do anything with it basically, but we will update this device that sent us this old gradient. We will send the current point that lives in server xk. We'll send it to the worker, and worker will start immediately computing gradient at this updated point. So hoping that in the future, this worker will be fast enough, or I mean the other devices will become slower, so the tau will change in some way, and potentially this device in the future can contribute. So when it will send you the gradient at this point xk, its delay will be smaller than r, so you will use it. So that's it. This is the whole idea of ringmaster actually. in this simple slide. So we have simple ASGD, and every time, instead of naively doing this update, every time we check if the delay is small enough. If it is, we do update. If not, we don't do it. And by this way, we will adapt dynamically, choose these fast devices. Okay. Questions?
Yeah, I will have one, but let me see whether somebody from audience have. If not, let me start with the first one. So is here gamma a constant or it depends on the delta K? Because that's what, as far as I remember, that with Mishenko and also Koloskova, I mean, they scale the step size by the inversely proportion to the delay. So would that make
Yes.
sense in your method, or you don't do it? You always take constant step size?
So in our case, we don't do that. And it turns out that including these old gradients, even with small delays, I mean, even with small gammas, with step size, it's also not useful, it's harmful. So you should actually ignore those, or you can put the gamma for this to be 0, actually. I mean, even having small learning rate for this old gradient is not good. And the key idea is that these delay adaptive methods, they are good. They are trying to improve things, but they are still greedy because they are still trying to use all the workers, all the gradients. And this remaster thing says that you shouldn't be that greedy. You should ignore some very, very old gradients completely.
I think I understood that, but what I thought is for the updates that you accept, whether you should not scale the step size also the same way proportionally to that delay, or whether
Yes,
that could lead to some improvement.
this is a very good question because this is what we are trying to do now for
Okay,
Murex.
I see.
Because even in the analysis, there is some point where potentially these gammas, which you don't ignore, potentially here you can do proportional to this delta K and on some other quantity, which we call MK, which let's say it's also something delta K. And we are hoping that we can do this in theory and we'll benefit from some constant factor, let's say, because this is optimal. I mean, you cannot beat it in up to constant, but let's say in constant factor we'll get some benefits, and also in practice it will be better because the idea makes sense. Because if the delay is smaller, it's some sense the gradient is better, and potentially for the step size should be bigger for this type of gradients.
I have just maybe
Right?
one small suggestion. I mean, maybe like other way how you can speed this up is because you wait till the worker sends you the update, and if their update is large enough, then you don't accept it and send them back the solution. But if you have some kind of like a global counter and they know that they already passed uh the deadline to submit, they can just download and start computing, which potentially I think at least practically can get you some extra speed up,
Yes,
right?
yes, yes. So in the ringmaster paper, we have two versions of these
Okay.
algorithms, and the second version is exactly what you said.
Oh, okay.
So
So,
in there we have delta I so
mhm,
we have delta I for each device, and every time once worker sends you a gradient, they simply increase their delta I
mm,
because their delay becomes bigger, and once they reach this threshold, all of them get synchronized
mm,
and start compute at new point. And I
got
mean,
it.
that's, as you said, in practice, that would be faster, but in theory, you don't get any benefit of doing that. And also, Sasha mentioned is that, so if you're doing, let's say, PyTorch or TensorFlow, it's not really clear how would you stop this process.
Okay.
I don't know this, but maybe it makes sense. So
Mm,
how would you stop your gradient computation, I guess, somewhere in the middle and restart this? Maybe it will take longer. Anyhow,
good. Thanks.
okay, thank you. Other questions?
I think you can continue.
Okay. All right, so this is ringmaster. What do we have next? Yeah, the question is now, how do we choose this threshold? So let's consider different values for this threshold. So what happens if we put r equals to 1? What happens? Can someone tell me what happens if r is 1? We are very shy audience today. Very little people.
That should be SGD, right?
Yes. It becomes SGD because it becomes this hero SGD where you use only the fastest worker. And that's just because every time this fast device sends you gradient, the delay for the others becomes bigger than, I mean, it becomes 1, and 1 is not smaller than 1. So you'll ignore all of them. And so you can also put R infinity. And if you do this, you will get this hog wild where you accept all of your gradients. So the sweet spot, so the optimal value is somewhere in between, and it's given in this formula. So it should be at least 1, because if it's smaller than 1, you don't have any updates. And it should be the sigma square over epsilon. And why it's sigma square over epsilon? It comes from the theory. So let's go to the theory and see what happens there. So we have this step size gamma, which is so 1 over 2 RL, and we choose this R to be, so this two minimums, they are exactly the same. So if you put sigma square over epsilon, you'll have I mean, these two quantities, they will be the same. So this is why we choose this gamma actually. And the iteration complexity for ringmaster is this, which depends on R. And if you have big R, then the number of iterations increases. And this makes sense. So if you cared only about the number of iterations, you would choose R1 and you would simply do SGD. And because you always do good updates. But if you increase R, you potentially you introduce these delays and potentially do bad updates. So you need to do more iterations to recover from it. But we don't care about this iteration complexity. What we care about is the time complexity. And this is the time complexity. We have almost the same thing as before of choosing these fast workers, but the only difference that here the quantities, the right-hand side is divided by epsilon. So let's look into this, what this says. So we have again this harmonic mean of tau i's. And as I said, these tau i's are ordered increasingly. And that's the same as if you increase m, this harmonic mean will also increase. And on the right side, we have another term which decreases with respect to m. And m, as I said, is the number of workers participating. So this introduces some trade-off. On the other hand, you want to include as many workers as possible. So you'll decrease this variance term. On the other hand, you don't want to include many workers because you will increase this harmonic mean. So let's consider maybe some examples. If you have all your tau i's are the same, then they are tau, then this harmonic mean will be tau, and this does not depend on m, and you would want to choose all of your devices. So this m would be n in this case. And if you have some tau i's that are infinity, then just adding this infinity term, which would be just to 0, you don't want to do that. And this formula will just not include those taus that are infinity. So that's the time complexity for this method. And this is for fixed tau i's only. In the paper, we also have the version where this tau i's can change arbitrarily during the process, during the training process. And for that case, unfortunately, we don't have a closed formula. And I guess you cannot have a closed formula because it depends on the behavior of this tau i's, and we assume that they can change arbitrarily. So that's why we don't have a closed form solution, but we have a formula, but we have something that depends on the rate of the change of this tau i's. Okay, Any questions?
So here, if I'm not mistaken, I mean, your R should depend on tauice. How is it the case that the formula that you present does not depend on the tauice?
Yes, this is a good question. We also got this question during the rebuttal. And and I mean that's true. The optimal R should actually depend on these taus. So let's say you have I don't know, tau 1 and the others are infinity, then in this case the optimal R should be 1, right? But our formula will say no matter what's happening, it should be the sigma square or epsilon, which is not really intuitive. But my answer to this is that if you choose 1 in this scenario, or if you choose the sigma square or epsilon, the difference would be just a constant factor. And basically that's it. We provide some upper bound or time complexity, which is optimal up to some constants. And yeah.
But then I'm very confused because since your R doesn't depend on tauice, shouldn't that be the case that regardless of what the tauice are, even whether they are changing, since my formula doesn't depend on that, it should be always optimal.
Yes, it's always optimal up to a constant.
Okay. And what that constant could be? Is there like upper bound to that constant? Like what is it? Is it like a I don't know, 5, 10, or
Yeah, I think yeah, it's something. It's not gonna be very big constant. Maybe 4.
okay.
Yeah, not a big constant. So the thing is that if this sigma square of epsilon is big, then I mean then it depends on this noise term, and you want to kill this noise term somehow, and that's why this R depends on that. Because if you have big R, then you are applying many gradients, and by doing that, you are killing this noise somehow.
Okay. And possibly, can you make it actually noise adaptive? Sorry, no, sorry, noise epsilon adaptive. Because I think I guess like you want this like a progressively converge to any level of epsilon because this one requires predefined epsilon, right?
Yes. So that's one of the ideas that we are working on now to make this adaptive to epsilon. And I mean, I think this is not difficult to do. We do this by doubling trig, let's say.
Mm.
So if we do for
Yeah.
some, I mean, instead of epsilon, if you had k, we do for
Mhm.
k, and then we do it for 2k, 4k, so on.
Yeah.
Or in this case, you would start from big epsilon and you would decrease by 2, I mean, divide by 2 every time. So you could get something like that.
Makes sense. Yeah, thank you.
And more questions? Okay, let me continue then. So some experiments. So here we compare renal SGD, which is also optimal, and this previous idea of delay adaptive SGD. And the important thing here is that Ringmaster is actually better in practice than Renala, even though they both have the same optimal time complexity. So they all have this upper bound, which is the same, so up to a constant. In practice, this Ringmaster is better. And the reason simply is that in case of Renala, you do this asynchronous batch collection, and then you restart all of your workers. In Ringmaster, so you do some updates, let's say you do R updates, and then you will restart the workers that have delay bigger than R, but you only restart the slow ones. I mean, you will only restart the ones that have bigger than R delay. But the ones that have smaller one, you will not restart them, and they will keep working. So the reason that this Ringmaster is faster, I'm assuming that is that exactly this, that you are not restarting all of your workers, but only the slow ones. Whereas in Renala, you restart all of them every time. Yeah, and delay adaptive, I mean, it's not optimal. Even Renala beats them, and that was the purpose of the Renala paper. They just showed that it's faster than this delay adaptive SGD for some tau-wise distributions. And yeah, the idea here that n is very big here. N is, I guess, 10,000. And in delay adaptive SGD, the time complexity depends on this n. And so gamma, the step size also depends on n, because this delta, if they don't ignore this all the gradients, the average delay will depend on n. And if you have many workers, you will do very small step size because you want to include all of your workers, and that's why in big many device scenario, this delay adaptive SGD would be worse. And so yeah, that's it. So how did we do this? We fine-tuned all the gammas and these R's, and we just plotted the best ones we found. And yeah, one more important thing here is that R and B are almost the same. And the reason is that the philosophy behind this R and B, it's kind of the same. Because in Renala, you do this asynchronous batch collection. In Ringmaster, instead of simply collecting this batch, you will actually do updates. You will receive this gradient and you will do updates. And then after you did this R updates, you'll ignore the rest. Same in Renala. You did this B collection, you'll ignore the rest. But not only the rest in Renala, you'll ignore the rest and also the things that the fast workers that are still computing something. And also gamma here, the difference in theory in gamma is R times smaller than the gamma for Renala. And we also can see it here. It's 5 times smaller, so almost like 6 times smaller. And it's also reflected in these experiments, which is good. Okay, any questions? We also did some deep learning experiments because during the
Just one
rebuttal, everyone
question.
was asking. Yes.
Yeah, is there a particular reason why a Ringmaster has significantly smaller step size than Renala? Is it also what theory predicts or no?
Yes, this is exactly what theory predicts. Theory says
Okay.
that this gamma should be so R times smaller.
Autumn, yeah.
In Renala, you have this. Then the reason is simple because in Renala, you take the mini batch, so you
Yeah.
do the sum of this gradient and divide it by B. But in Ringmaster, you just have the sum of these gradients.
Yeah,
You don't
makes
actually
sense
divide
because
them
you
by
do
R.
update every time, right? Like you never
Yes,
wait for
yes, yes,
anybody. Yeah,
yes, yes, yes,
yeah, makes sense. Thanks.
yes. Okay. So this was the last slide. So now let's recap what we've done. So we started from this stochastic optimization objective. We want to solve this. We said we have this heterogeneous system. We have different workers. Everybody has access to this distribution D of this size, and everybody can calculate unbiased gradient of this f loss function, and the variance is of all of this f is the same. It's bounded by sigma, but the difference is that these devices they have different computational times, and which we denote by this tau i's. And the question was, how can we do SGD on if we have these workers available to do it as fast as possible? So we first discussed this synchronized approaches. The first one was hero SGD, where we ignore the slow ones and we only use the fastest worker. And in this case, it will depend on the time of these fastest workers and the number of iterations you do. But potentially, we said that you could use the other workers and it can be faster. So then we did exactly that. We used all the workers and we did mini batch SGD. And here every iteration depends on the slowest worker. And then we went one step further. We said we don't really care which worker sends you gradient. So why do we do this mini batch SGD? Why do we ask one gradient from all the workers? Let's just do again mini batch SGD with some batch size B, and do this batch collection asynchronously, which would be the fastest possible way to collect this batch. And that's Renala. This also has the optimal time complexity, but we noticed that all of these approaches we have some gaps where we don't use these times basically, and we say, what if we try to use this time and maybe we will get something better if we do that. So that would be this asynchronous SGD, where we do update every time a worker finishes its computation, and that's the Hogwild paper first introduced Hogwild this idea. And the problem here is that we cannot write anymore this update as stochastic gradient in this sense, and we need to do something with this. We need to even try to analyze this, and this algorithm has a problem, and the problem is that it has delays, and these delays can be harmful. And as we've seen in this example, if you have updates with big delays, you can do very bad updates. So you need to decrease the step size, or what we did in Ringmaster, we decreased the delay actually by ignoring some gradients, and we said, this is, I mean, the hog wild was wild. We need to tame it. The way we tame it, we simply ignore those bad updates. And this was the simple ringmaster. We received gradient from some worker. We check if the delay is smaller than some threshold. If it is, we do the update. If not, we update the slow worker, hoping that in the future it may contribute. And this gave us optimal time complexity. So this was ringmaster. That's it. So let me acknowledge my co-authors, Sasha Turing from Skoltech and Peter Tarek, my PhD advisor. Yeah, now let me just quickly mention some closely related papers. There are more papers from our group, and if you want to get the general picture of these papers, you can check Peter's talk, which was on Flow last week. But I'll mention just these two because I'm one of the authors here, basically. So the first one is Mind Flare. This is with Omar and Peter. And here we consider Rinala, but these tau i's, we assume that they are not constant, they're not deterministic, they are a random variable, and they can also be, they can have heavy tails, their distribution can have heavy tails. So, for example, what is the practical example of this? Maybe the worker sends you a gradient, but it never receives because of some network issue. So and the time in this case, we say it's either fixed tau or infinity if something went wrong. So in this case, it turns out you can do something to fix this processor, and you also do some thresholding here actually, but you threshold the time. Okay, anyways, and we have another paper, this ATA paper, Adaptive Task Allocation, with Almedi, Peter, and Francesco. And this is somehow a bit different than all of this stuff. And here we focus on the idea of minimizing the number of resources spent, because in this, if you do asynchronous batch collection, you are wasting many computational resources because every worker just computes something. Let's say you have 1,000 workers, you want only 10 gradients, but you every time ask all of your workers to compute this gradient, and you simply take the fastest 10. And so you will discard all of the others. So here we will try to minimize this wasteful computation by trying to find which workers are the best, are the fastest. And we do this by online learning, by bandit theory. So we construct some confidence bounds for their times, and we do some UCB, some online learning bandit stuff. So that's a very interesting paper actually, and if I have a chance, I can also talk about this. Okay, let me finish with this. So even though there is more than a decade of research on this asynchronous SGD methods, there are still many things that we don't understand about this asynchronous stuff. So let me invite all of you to join me in this journey of trying to understand even further this asynchronous SGDs. That's it. Thank you.
Thank you, Arto. Are there any questions? Yeah, there's a question by Igor, since he posted it in the chat. So let me just read it out loud for you. How sensitive are these methods with respect to the choice of hyperparameters, for instance, step size in practice?
Well, we didn't, so let me say that we didn't test this intensively in practice. We only did this experiment, this logistic regression experiment. And for that, I can say that it is not really sensitive to the step size. And I mean, to be honest, we didn't have a very big window of step sizes, but still it was not that sensitive. But this method requires further investigation for practice, I would say, because we simply didn't focus on that.
And do you have an idea on how much method would change if you assume that now now the clients might be heterogeneous, so they compute slightly different gradients?
Yeah, that's a good question. And we don't know. We don't know what we can do about this. It seems it's not that easy. So even the previous methods, this delay adaptive SGD, they do analyze this scenario where you have this heterogeneous, this federated learning scenario, basically, where each worker has different distribution, right? And there they assume some similarity between this, and their rate depends on similarity. So we were trying to avoid this similarity because in this Renala paper, they have the version, this heterogeneous version, where they also achieved optimal time complexity, but without any similarity assumptions. But it seems that it's not easy for full asynchronous methods to analyze them without any similarity assumptions. So we currently don't know what will happen.
Okay, yeah, thank you. I think we are right on time, but maybe we have time for one more question, if any. If not, yeah, thank you, Arto, again. It was a very nice talk. Pleasure to host you, and yeah, hope to see all of you in the next seminar. Thank you once
Okay.
again, and
Thank
have
you very much.
a good rest of the day. Bye bye.
Bye.